Hello everyone, welcome back to the lecture sessions on infinite series. Now in the last session, we have defined infinite series and have introduced to you the concept of convergence and divergence of a series. Let us take a quick review of that concept first. Now see that we have seen that in order to define or examine a given series is convergent or divergent, we first need to construct the sequence Sn of its partial sums and check the convergence or divergence criteria of this sequence of partial sums. Now, if this sequence Sn is convergent and converges to a limit L, then the series summation n equal to 1 to infinity An will be said to be convergent, and also it converges to L. In fact, the sum of the series in this case is given by L. Similarly, for divergent series also, we have to proceed in a similar way. And if the sequence of partial sums is divergent, then we say that the series is also divergent. The third one in this list is the oscillatory series, and a series summation n equal to 1 to infinity will be said to be oscillatory if the sequence of partial sums is also oscillatory. In other words, if the series is neither convergent or divergent, then we will say the series is oscillatory. Let us now examine some series to check whether they are convergent or divergent or oscillatory. So we have one over here. Investigate the convergence of the series summation n equal to 0 to infinity log n plus 2 by n plus 1. So as we proceed, I hope we understand that first we have to construct the sequence of partial sum Sn, right? So for that, first let us notice that An, the nth term, is log n plus 2 by n plus 1. So this is nothing but log n plus 2 minus log n plus 1. And as we go to construct Sn, let us also note that this series starts with n equal to 0. So as we will construct Sn will be actually starting from A0 plus A1 plus A2 plus An. So A0, as you put n equal to 0, A0 will give you log 2 minus log 1. A1 will be log 3 minus log 2. We continue like this. And the last term, the nth term, is of course log n plus 2 minus log n plus 1. So you see here what is happening, that log 2 and log minus 2 here will cancel. Log 3 and minus log 3 will cancel. So it will go on happening like this. So at the end, we will be left with the first term minus log 1 and the last term log n plus 2. And we all know log 1 is 0. So therefore, this is nothing but log n plus 2. And now what do? Of course, we have to take the limit as n tends to infinity. So as Sn is log n plus 2, so as n tends to infinity, the limit is also infinity. So thus, we see that the sequence of partial sums is actually divergent because the limit is infinity, and hence we conclude that the given series also diverges. We have another example for you here. Investigate the convergence of the series 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on, which in the concise notation may be written as summation n equal to 1 to infinity minus 1 to the power n minus 1. Now, of course, here also we have to look into Sn first. But for that, notice one thing, that the terms are such that if we add even number of terms, say first two terms, or first 4 terms, or first 6 terms, the sum is going to be 0. So when you take an even number of terms, the sum is going to be 0. However, if we add odd number of terms, so say n equal to 3, the sum is 1. If we take n equal to 5, the sum is also 1. So therefore, we can write that Sn will be 0 if n is even and 1 if n is odd. So how does the sequence look like then? Then the sequence looks like The elements are like this: 1, 0, 1, 0, 1, alternatively 1 and 0. And if we observe carefully, this is an oscillatory sequence. Why? Because see that a sin is not having a fixed expression. It is either 1 or 0 depending on n is odd or even. So as we take the limit n tends to infinity, we don't have any finite limit because limit has to be unique. Limit cannot vary between two numbers. So therefore it is not a convergent sequence, even it's not a divergent sequence. So this is the case of an oscillatory sequence. And now because the sequence of partial sums is oscillatory, obviously the given series is also oscillatory. Let us now look into two very important infinite series which will be very much useful in our subsequent discussions. So the first one here is geometric series, summation n equal to 0 to infinity x to the power n, that is 1 plus x squared plus x cubed. The general term is of course xn and so on. And now we have a very important result for you which tells when this series will be convergent or divergent or oscillatory. So what is there? The geometric series summation xn is convergent if x lies between -1 to +1, divergent if x is greater or equal to 1, and oscillating if x is less or equal to -1. So if we think of the number line and the open interval -1 to 1, see that within this interval the series is convergent. If we go to the right, so x is greater or equal to 1, it is divergent. And if we go to the left of this interval, the series is oscillatory. So this is a very, very important result to be remembered. And how it's happening, why it is so, this will be a homework for you. Try to prove it yourself. And as a hint, I can say that as we had been looking into the problems before, similarly here also, of course, you have to do nothing but construct Sn and then try to prove this by taking limit of Sn as n tends to infinity. The next one in this line will be the P series. What is that? It is summation n equal to 1 to infinity 1 by n to the power p. That means if I talk about it explicitly, 1 by 1 to the power p, 1 by 2 to the power p, 1 by 3 to the power p, 1 by n to the power p, and so on. Now, when does this series converge or diverge? So the P series is convergent if P is greater than 1 and divergent if P is less or equal to 1. So once again, this is an important result to be remembered. The P series converges for P greater than 1 and diverges for P less or equal to 1. Now note one thing, if P equal to 1, what happens? P equal to 1 actually gives you the harmonic series, right? So this is 1 plus half plus 1/3 plus 1 by n. And then we take a note from here that if P equal to 1, the series actually diverges. So again, we should remember that the harmonic series is a divergent series. Again, an important result to be remembered. Next, let us look into some properties of an infinite series. The first one, property number 1, if sigma an is convergent and converges to S, then sigma kn is also convergent and converges to Ks, where K is a constant. So what does it mean? That means that if we have a convergent series whose sum is S, and now every element of the series is multiplied by a constant K, then still the series remain convergent. And the sum of the series is now just also multiplied by K, so it is Ks. The property number 2, if sigma an is divergent, then sigma kn is also divergent where K is a constant. So if your series was divergent and having an infinite sum, Now if you multiply the terms of the series by k, it will be of course divergent. Property number 3, if sigma an and sigma bn are convergent and converges to S1 and S2 respectively, then the series summation k1an plus k2bn is also convergent and converges to the sum k1s1 plus k2s2, where k1 and k2 are constants. So let us understand this property a little bit carefully. So you have two convergent sequences, summation an and summation bn, and their limits are s1 and s2. Now see, as by the property number 1, if summation an is a convergent sequence, then of course summation k1 an for a constant k1 is also convergent. Similarly, summation k2 bn is also convergent. And now what it says, that if we are adding up two convergent sequences, then the sum will be also convergent, and the sum will be simply given by the sums of the individual series. And the last property in this line states that the character of convergence or divergence of an infinite series remains unaltered by the addition or removal of a finite number of its terms. So what does this mean? This means that if your series is convergent, then if we add a finite number of terms to it, or if we remove a finite number of terms, still the series remains convergent. On the other hand, if your original series is divergent, then also adding or removal of a finite number of terms does not affect its character. It still remains divergent. Next, we will see two important results in terms of two theorems. So, the theorem 1 is as follows. If the series summation an n equal to 1 to infinity is convergent, then limit an n tends to infinity is equal to 0. This is a very important result to be remembered, that for a convergent series, it always happens that as n tends to infinity, an tends to 0. Let us see the proof of it, how it happens. Now, of course, first we need to define the partial sum Sn, which is a1 plus a2 plus a3 up to an. And then Sn minus 1, this will go up to an minus 1, right? So this is a1 plus a2 plus a3 plus an minus 1. So then we see that if we subtract these two, Sn minus Sn minus 1 gives us an. And since the series is given to be convergent by definition of convergent series, of course the sequence Sn of partial sums must be convergent. And let us now assume that limit Sn n tends to infinity is equal to S. Then we try to find out limit an n tends to infinity. And now in place of an, we have put Sn minus Sn minus 1. So using the property of limits, this can be written like this: limit Sn n tends to infinity minus limit S of n minus 1 n tends to infinity. Now limit Sn n tends to infinity is S. What is this term? See that as n tends to infinity, n minus 1 also tends to infinity. So therefore limit Sn minus 1 n tends to infinity is nothing but S again. So this becomes S minus S, and finally limit an n tends to infinity is 0. So we have proved the result, and see that this is a very important result and can be often used in examples to test the convergence or divergence of a series. And observe that if for a series we find limit an n tends to infinity is non-zero, we can easily conclude that the series is not convergent, because for a convergent series we always have limit an n tends to infinity equal to 0. But we should take note of a very important thing, that the converse of this theorem is not necessarily true. That means limit an n tends to infinity equal to 0 does not necessarily imply that the series is convergent. See once more, if the series is convergent, then limit a in n tends to infinity must be 0. But the limit equal to 0 does not imply that the series is convergent. And a very common example of this is your harmonic series summation 1 by n. We have already seen that this harmonic series is a divergent series, but see that here, because an is 1 by n, so limit a in n tends to infinity is equal to 0. So please be cautious about this result. The next theorem, a series of positive terms either converges or diverges to plus infinity. It cannot be oscillatory. So if your series contains only positive terms, then it cannot be oscillatory. Now, of course, because it is containing all positive terms, there is no chance to go to minus infinity. And if it converges also, it will converge to a definite finite limit. So a series of positive terms either converges or diverges to plus infinity. With this theorem, we will close today's session, and in the next lecture session, we will see more about series of positive terms, or we call it just positive series. So, thank you and goodbye till then.